So let's review periodic trends by doing an assortment of practice problems. So periodic relationships amongst the elements. So some chapter 8 examples taken from your textbook. The first one is a neutral atom of a certain element has 20 electrons. So neutral atom means it's not an ion, has a charge of 0. 20 electrons means if it's neutral, the number of electrons is equal to the number of protons. So 20 electrons here is going to be calcium. So this is referring to calcium. And it's asking for the ground state electron configuration of calcium. So remember how will the electrons march in for calcium, which is the identity of the element with 20 electrons. It's going to be 1s2, 2s2, 2p6, 3s2, 3p6, 4s1, 4s2. So it's going to be argon 4s2. So the element here is calcium, and it's argon 4s2. Okay, I'm not going to write out all of argon, but if you want to write out all of argon, it's going to be, like I stated before, 1s2, 2s2, 2p6, 3s2, 3p6. That's all of argon. I'm not going to write all of that for argon. I'll just say argon 4s2. By the way, this is not called the ground state. This is called the condensed electron configuration, because I'm not writing all of the other electrons in there. Classifying the element calcium is in group 2A, so this is an alkaline earth metal. By the way, I'll just change my mind here. If you want to, since I'll answer the question, instead of giving the condensed version, I'll give the ground state version. Argon is going to be 1s2, 2s2, 2p6. Remember, the electrons are going to march in a very specific order. First 1s, then 2s, then 2p. After they fill 2p, they'll fill 3s. And then after filling 3s, they're going to fill 3p. And then 4s2 is left behind, and that represents calcium. So this is the ground state shown here, and then shown above is the condensed state. Determine whether the element is diamagnetic or paramagnetic. Since the electrons are paired, I believe this is paramagnetic. Diamagnetic would mean that you have unpaired electrons. So diamagnetic would be unpaired. Paramagnetic would mean the electrons are paired together. No unpaired electrons. This would be a paramagnetic species. Write the electron configuration of these ions. Calcium plus 2. Well, this should be easy, hopefully by now. Losing 2 electrons in calcium. Here is calcium right here in the 4s2. Loses those 2 electrons. It's going to have the same electron configuration as argon. Okay? And we already know argon has this electron configuration in its full ground state. S minus 2. S minus 2 is the same thing. Gaining 2 electrons, it will have the same electron configuration as argon. 16 electrons in S minus 2 gains 2 electrons. It will be the same electron configuration as argon. So in fact, we can call these 3 elements, calcium plus 2, S minus 2, and argon, isoelectric. Next question here in this series from your textbook. Write 5 species of the isoelectronic same electron configuration. That is 36 electrons. So first let's look and see what exactly is 36 electrons. 36 electrons is going to be krypton. So we have several elements here that have the same electron configuration as krypton, or that can have the same electron configuration as krypton. So just off the top, looking at our sheet here, one would be Br minus, Se minus 2. So one would be Br minus, Se minus 2. And let's go here. Krypton, right? So krypton, how about rubidium plus 1 and strontium plus 2? Anything else we can think of? For krypton, I can think of yttrium, Y plus 3. We can do As minus 3. So there's a whole bunch that are isoelectronic. It asks for 5, and actually krypton and all these other 5 have the same electron configuration. Decreasing atomic radius. So remember our trend here, okay, as we review. Remember our trend for atomic radius. The atomic radius increases from right to left in the periodic table, because here you're getting more of the valence, outer electrons. Here the electrons are more tucked in. And the the atomic size, or the atomic radius, increases as you go down, okay, increasing principal quantum number. and that would mean increasing energy levels, increasing radius as the electrons move to the outer, and more outer electron shells. So looking at carbon, lithium, and beryllium, this pretty much is the trend here. Carbon, lithium, and beryllium. Let me highlight this here. We have carbon, we have, we have lithium, we have carbon, and we have beryllium. So obviously lithium, going by the trend, lithium is going to be largest. Beryllium would be second largest. Carbon, these tend to be small in this regime of the periodic table. Carbon would be the smallest here. The order here, decreasing radius, would mean carbon would be so largest to smallest, right? So lithium would be the largest, and then beryllium, and then carbon. Okay, the more metallic it is, the larger it is. More of the nonmetals are pretty small. Here we're asked to look at size of the ion. This is different than the previous problem, which is atomic radius. Here we're looking at the ionic radius. So potassium and lithium. So here, positive charge loses electrons, so they're going to be smaller. But we're looking at lithium and potassium. First, I would say compare the uncharged. Lithium is going to be larger than lithium is going to be smaller than potassium. N equals 4 and N equals 2 in terms of the shells. 4s and then 2s. So potassium is going to be larger. Lithium is going to be smaller. By itself, no ions. Once you lose an electron, you become even more smaller. So lithium plus is going to be much smaller than potassium plus. Okay, lithium by itself, neutral, is already smaller than K, potassium. Gold is Au plus 3 versus plus 1. Obviously, if you lose 3 electrons and all of that associated electron density, you're going to be smaller. So Au plus 3 is smaller than Au plus, because obviously if you lose 3 electrons and its associated electron density, you'll be smaller as compared to losing only 1 electron. Here you're gaining 3 electrons, so what you want to do in this situation is look at the neutral elements without ions. So nitrogen is going to be smaller than phosphorus. As you go down the group of the periodic table, you get larger and larger N, larger and larger principal quantum numbers. So nitrogen is smaller. N minus 3 is going to be even more smaller than P minus 3, because N is already smaller than P. So N minus 3 is smaller. First ionization energy, so IE1, the energy required to not flip, but to remove or strip an electron. So which one of these should have a larger ionization energy? The ionization energy is going to increase left to right in the periodic table. It's going to increase down to up in the periodic table. So which one will have a larger first ionization energy? And the one that will have the larger first ionization energy here is nitrogen and phosphorus. Nitrogen should have the larger first ionization energy. As you go down, you get more outer, and outer, so it should have a larger first ionization energy, nitrogen. Smaller second ionization energy, sodium or magnesium. It's going to be magnesium, right? Because magnesium, if it loses 1 electron, it's going to take a lot of energy. Losing 2 electrons, it becomes noble. So it takes less energy to remove that second electron. A smaller first ionization energy, phosphorus versus sulfur. So phosphorus, if we look here, this is in N equals 1, N equals 2, N equals 3. So it would be N equals 3 phosphorus, and then sulfur, so 3p1, 3p2, 3p1, 3p2, 3p3. That would be for phosphorus. And then let's do the 3p electrons for sulfur, 3p1, 3p2, 3p3, 3p4. 3p4. So it's going to take a lot more energy to remove this electron because this is already stable by itself. So sulfur will have a larger first ionization energy, and phosphorus would have a smaller first ionization energy. Right? It takes a lot of energy to remove this electron in sulfur, 3p4, than it is for phosphorus. It's going to take a lot of energy to remove this from phosphorus, that 1 electron, because again, this already by itself is pretty stable. Electron affinity, electronegativity and electron affinity, boron versus carbon. The trend is as you move this way in the periodic table, you become more and more electron affinity. definitely in the halogens, definitely the noble gases. So carbon should have a greater electron affinity, or in other words, electronegativity. So this would be greater, and the question is which is smaller. So boron would be a smaller electron affinity. Larger electron affinity, electronegativity, silicon versus phosphorus. Definitely going this way, phosphorus will tend to cling on to electrons more than silicon. So the larger electron affinity here is going to be phosphorus. And then finally, we ask ourselves the question, is it likely for argon to form the anion Ar minus, and then flat out never? Okay, it's not going to form. Noble gases, of which argon is a part of, will never ever form charges, positive or negative. It has a completely filled electron shell. In fact, if you look at the periodic table, argon will have a completely filled 3s shell, the s2, 3p6.